Hello everyone. Now let us discuss about AVL trees in data structures. So in this video, I'm going to discuss about introduction to AVL trees and various rotations that can be performed on AVL trees like left rotation, right rotation, left rotation and right rotation. So in the previous video, I implemented the C program for creating the binary search tree. So please watch it before watching this video. An AVL tree is defined as a self-balancing binary search tree where the difference between heights of a left and right subtree for any node cannot be more than 1. So in the term AVL tree, AVL stands for Adelson, Wilsky and Landis. These two are the inventors of the AVL tree data structure in the year 1962. The difference between heights of left and right subtree is known as the balance factor. So, a tree is considered to be balanced if every node in the tree has a valid balancing factor. So, by considering the given tree, let us consider one node which is 12. The height of left subtree for the node 12 is 3, which is 8, 5 or 11 and 4. Similarly, the height of a right subtree for the node 12 is 2, which is 18 and 17. So the balancing factor for the node 12 is height of left subtree minus height of a right subtree, which is 3 minus 2, which equals to 1. So node 12 is balanced. Similarly, we will check the balancing factor of all nodes. If all nodes are balanced, then we can say that the entire tree is balanced. So this is the brief introduction about the AVL trees. So while inserting or deleting a nodes from the tree, first we will check the balancing factor for that particular node. If the balancing factor is not in the range between -1 to +1, then we perform rotations for the subtrees. So there are total 4 types of rotation. The first one is left rotation. So in this, let us consider we have a node 30, two nodes in the left subtree, which is 20 and 10. So first we will check the balancing factor for the bottommost node, which is 10. So for the balancing factor for the node 10 is height of left subtree minus height of right subtree, which is 0, which is a balancing node. Now we will check the balancing factor for the node 20. Height of left subtree, which is 1, and height of right subtree, which is 0. 1 minus 0, which is plus 1. So node 20 is also a valid balancing factor. Now we will check the balancing factor for the node 30. So the height of left subtree, which is 2, minus height of right subtree, which is 0. 2 minus 0, which equals to 2, which is not a valid balancing factor. So to achieve balance for this tree, we perform a right rotation between node 20 and 30 so that the 20 becomes the root node and 30 becomes the right subtree for the node 20. So now we will check the balancing factor for each node. So now the tree is balanced. So this is about left rotation. Now let us look at the second type of rotation, which is right rotation. In this, let us consider we have a node 10. It has no left subtrees and two, two nodes in the right subtrees, which are 20 and 30. First, we will start from the bottommost node. We will check the balancing factor for the node 30. Height of left subtree, which is 0, minus height of right subtree, which is also 0. So node 30 has a valid balancing factor. Now let us check the balancing factor for the node 20. So for the node 20, the height of left subtree, which is 0, minus height of right subtree, which is 1. 0 minus 1, which equals to minus 1, which is also a valid balancing factor. Now we will check the balancing factor for the node 10. It has no left subtrees, so height is 0. The height of right subtree, which is 2. So 0 minus 2, which equals to minus 2, which is not a valid balancing factor. So to achieve balance, we perform right rotation. So in this, we perform left rotation between nodes 10 and 20. So now 20 becomes the root node and 10 becomes the left child for the node 20. Now again we will check the balancing factor, which is 0 for every node, which is a valid. So now the tree is considered to be a valid balanced binary search tree. So this is about right rotation. Now let us look at the third type of rotation, which is left right rotation. So in this, we will consider three nodes where 30 is the root node and 10 is the left child for the node 20 and 20 being the right child for the node 10. So we will start from the bottommost node, which is 20. We will check the balancing factor, which is height of left subtree 0 minus height of right subtree 0. 0 minus 0, 0, which is a valid balancing factor. Now we will check the balancing factor for the node 10. Height of left subtree 0 minus height of right subtree, which is 1. So 0 minus 1 minus 1, which is a valid balancing factor. Now we will check the balancing factor for the node 30. So height of left subtree, which is 2, and then minus height of right subtree, which is 0. 2 minus 0, 2, which is not a valid balancing factor. So to achieve balance, first we perform right left rotation between nodes 10 and 20, and then we perform right rotation between nodes 20 and 30. So observe the process between step 2, 3 and 4. So finally the 20 becomes the root node and 10 is the left child for the root node 20 and 30 is the right child for the root node 20. So and then we will check the balancing factor for each. So now the AVL tree is balanced. So this is about left right rotation. So now let us look at the final rotation, which is right left rotation. So in this, let us consider a tree where 10 being the root node and 30 is the right child for the root node 10 and 20 is the left child for the node 30. So initially we will start with the bottommost node, which is 20. We will check the balancing factor, which is 0. And then we will check the balancing factor for the node 30, which is height of left subtree 1 minus height of a right subtree, which is 0. 1 minus 0, 1, which is a valid balancing factor. Now let us check the balancing factor for the node 10. Height of left subtree 0 minus height of a right subtree, which is 2. 0 minus 2 equals to minus 2, which is not a valid balancing factor. So to achieve balance, we perform right rotation between nodes 20 and 30, and then we perform left rotation between nodes 10 and 20. So observe step 2, 3 and 4 for better understanding. So finally the 20 becomes the root node 10 is the left child for the node 20, and 30 is the right child for the node 20. And then we will find the balancing factor, which is 0 for all nodes. So now this tree is considered to be a balanced AVL tree. So these are the four rotations that are involved in balancing a binary search tree. So this is all about AVL trees. So thank you for watching this video. Please like, share and subscribe to our channel. If you have any doubts regarding this AVL trees, or if you want to provide any feedback, please comment below. Thank you for watching.